So we've talked about some energetic events, celestial events. We've talked about a nova event, two types of supernova events. And now we need to talk about quasars. And quasars are the most energetic event, I guess they would say, in the universe. And basically, what we believe now quasars, or what they believe quasars is a supermassive black hole that is feeding. Now there might be other sources of quasars, but that's the one I want to focus on. We've talked about how most galaxies have a supermassive black hole in their center, and if it has material falling into it, basically I have a slide here in a minute to kind of show you the accretion ring of material that's kind of in queue to fall in, and that heats up and we get all sorts of energy from that. So that's what quasars are. Most quasars we see are way far away from us, and that's because, I'll go ahead and put these spectra up here. At the bottom of the spectra is what we expect those spectral lines to be. And the top spectra is showing you the redshift in this quasar event. So they're located a fair bit of distance from us. And the reason that is because quasars are more common back early on in the history of the universe. And so with regard to energy of an active galactic nucleus, the energy released by a quasar event is like 1 trillion times, or 10 to the 12th, the energy that's released by our sun. So, yeah. What you're looking at here is a galaxy that was, like the slide said, that galaxies can be disturbed. Galaxies in the vicinity of quasars can be a shock wave can impact them. So I know that if you watch those videos on the History Channel about how Earth can be sterilized or no longer livable, that's one of them, is we can be caught up by energy from a quasar, from a galaxy that becomes speeding again. So here is kind of the spectrum of energies that are released by a quasar event, and you can see that the red line is intensity, and of course along the x-axis we have an assortment of wavelengths. So radio galaxies then kind of focus on those longer wavelength energies that are released. So you see here, I think this is kind of neat, you see here this is the visible galaxy that's feeding, and then we can't see these plumes of energy and material, but here in the radio region of the electromagnetic spectrum we can see the material being ejected out, and the material that's ejected is moving at about the speed of light. So here's kind of another a similar radio galaxy, where radio galaxies are actually showing us a quasar event where a supermassive black hole will be right here, because this is kind of like the disk of the galaxy, and we see the material again shooting outside of the disk in both directions. So this is kind of neat. It's showing us again the the ejected material from 91 to 93 to 94 to 96. 97, and those blobs of they don't look like they're going very far in these 6 years worth of photographing it, but these are at very great distances, and those blobs are traveling at the speed of light, or very nearly the speed of light. So we would expect then that what created this, or this, I guess we would call it a radio galaxy here, what's created this ejected material is a feeding black hole. So again, here is we would be looking at it kind of edge on, the galaxy edge on. So the supermassive black hole is in the center there. You can kind of see the ejected energy from kind of the top of the disk and the below the disk. And actually, our black hole in the middle of the Milky Way galaxy and I can't remember how many years it's going to be. Maybe it's not that far from now, but there is a star in queue to kind of get torn apart and fall into, get basically kind of spiral down towards and into the supermassive black hole in the center of our galaxy. Remember, we call that Sagittarius A star is our black hole. But I don't know. So remember then that energies associated with quasars are generally what we call the galaxies being active. More specifically, the black hole in the nucleus of the galaxy is being active. And a lot of energy can be released, and it's released quickly with a variety of wavelengths, and we can get plasma shooting out both sides of the disk. So I mentioned this before, that what we think is powering this quasar event that we see from our perspective is matter that is in an accretion disk, basically in queue to fall into the black hole. And then not to mention the energy released as matter falls into the black hole. That whole eating, it's got to, the black hole burps, basically. So this is kind of looking what we've been talking about, where you see this would be, kind of take that pink and extend it outward. That would be like the disk of the galaxy itself. And there's the supermassive black hole in the middle of the galaxy. And then you can see as it feeds, it gets jets of material going out both sides. So just to kind of remind you, this is actually a slide from the previous chapter where we said we know that we have a supermassive black hole in the center of the Milky Way, we call Sagittarius A star, simply because we can look at the motion of the stars in orbit about it and get a handle on its mass, and then we can then confine that to a certain volume, and we know its density must be a black hole. And we can do similar things looking at kind of this face-on sort of situation of this particular galaxy. Look at the orbital pattern of these stars orbiting its black hole in the center. And we know that it has a black hole based upon its density. And I think I've been saying this for a little while now. Even relatively small galaxies, they think now have supermassive black holes. But the smaller the galaxy in general, probably the dinkier the supermassive black hole. And you can tell kind of to a certain extent what sort of black hole is being harbored in the center of a galaxy by looking at the bulge, the nuclear bulge. Like this slide says that while those with smaller nuclear bulges, that would be the bulge in the center of the galaxy, harbor small black holes. The larger the nuclear bulge, then it means the larger the black hole.